Thanks for the great introduction given by Lokesh. I'm going to tap into some technology technical details for the PFAS remediation projects brought up by the CCWT. And okay. So first I'm going to introduce the destructive PFAS remediation technologies using the vacuum UVs. When we are referring to the vacuum UV irradiations, we're usually referring to the irradiation with the wavelengths less than 200 nanometers. And we know that with the shorter irradiation wavelengths and the higher energy of the photon being generated, with the vacuum UV 185 nanometers, we have the emitted photons with the higher energy as 646 kilojoule per mole, which is higher than the carbon-fluorine bond dissociation energy and capable of destructive PFAS. In addition, the vacuum UV is capable of interacting with water and oxygen to generating the reactive oxygen species, such as hydroxide radicals, hydroelectrons, and ozones. And those reactive species is strong oxidant or reductant, capable of furthering reacting the targeted compounds in the waters. However, the applications of the vacuum UV into the PFAS treatment have several limitations. First is because it has very low degradations for the sulfonic compounds. A previous reference showing 1 ppm PFAS, PFOS, would require 72 hours to reach 80% of degradations. And also because the complex nature of the intermediates, the reactive intermediates, so the mechanism is complex and understudied. Excuse me. So our primary research objective for the vacuum UV irradiation is first, we try to understanding the detailed degradation mechanisms for the carboxylic compounds and sulfonic compounds. And also, we want to further optimizing the vacuum UV operational conditions for PFAS degradations, such as pH, oxygen, radical quenchers, and additive photosensitizers. Finally, we're trying to improving the overall degradations for the PFASs using vacuum UV degradation, including both sulfonic and carboxylic compounds, short chain and long chain compounds under the optimized clean conditions. So thanks to previous great talks about the PFAS background, we all know that PFAS is a big family with more than thousands of chemicals. And depending on the structure, chemical structure of PFAS, we can characterize that into subgroups, such as carboxylic compounds as PFOA and sulfonic compounds as PFOS. And also, depending on the carbon chain length, we can characterize that as the long chain PFAS and short chain PFAS. Here, we first employ 4 PFAS model compounds, PFOA, PFHXA, PFOS, and PFHXS, to performing the vacuum UV degradations. From our preliminary results, we observe that the PFOA have high degradations within 4 hours vacuum UV irradiations. In comparison, the sulfonic compounds PFOS and PFHX has much less degradation compositions under 4 hours irradiations. So we conclude that the vacuum UV is actually effective, highly effective for carboxylic compounds degradations. However, it is ineffective for the sulfonic compounds degradations. In addition, we examined the chain length dependence impact on the PFAS degradation using the vacuum UVs. We observed that as the carbon chain length decreases, the PFAS degradation rate decreases as well. So we conclude that the vacuum UV is more effective for the long chain PFAS decomposition compared to the short chain PFAS decompositions. That is also one of our research goals. We wanted to understanding the previous observed observations by tapping to the vacuum UV photolysis mechanisms. We know that upon the light irradiations, it will generating high energy photons, as well as it will break down the waters into the hydroxide radicals and the hydroelectron radicals. And also it's reacting with oxygen to generate ozones. From a previous reference, we know that hydroxide radicals and the ozone itself cannot decompose the PFAS. So it's leave the high energy photons and hydroelectrons as two major species break down the PFAS in the vacuum UV environments. And first, we are examining these degradations in the air condition. And some of you probably know that air is the effective quencher for the hydroelectrons. So in the presence of air, we remove all the hydroelectrons in the systems, and the photon is the only active species to degrade the PFAS. At the same time, we increase over pHs, which increase the hydroxide ion concentrations. We know that hydroxide ion is capable of absorbing the vacuum UV 185 nanometer. So increasing the pH concentration will decrease the photons in the system. And we observe that the PFOA decomposition rate is actually decreases when we increasing the pHs. And also we observe that degradation for the softening compounds is actually unchanged. So based on the above observations, we conclude that the photons is the major reactive species for PFOA degradations. However, it is ineffective for the PFOS degradation. And further, we examine the degradations in the argon ambient, which is in the absence of air. So in the absence of air, we know upon the light irradiation, we will have two reactive species, both photon and hydroelectrons. And in that situation, when we're increasing over pH, we're decreasing the hydrogen ion concentration. Some of you might know the hydrogen ion is actually another effective quencher for hydroelectrons. So when we increasing the hydrogen ion concentration, the hydroelectron concentration actually increases. We're increasing the pH, decrease the hydrogen ions, and increases the hydroelectron concentration. And also, when we're increasing the pH, the hydroxide concentration increases. We just mentioned the photon concentration is going to be decreased. So now let's look at the PFAS degradations in the anaerobic condition. We notice that we observe different trend for the PFOA degradations in anaerobic conditions. We see that as the pH increases, PFOA is actually increases. And also the PFOS significantly increases when we increase the pH. As we know that when we increase in the pH, the reactive species increased is hydroelectrons. So here, based on the observation, we conclude that the hydroelectron is the major reactive species for both PFOA and PFOS degradations. And based on our observations, the results, we conclude that the hydroelectron concentrations is one major pathway to optimize the PFAS degradations for both carboxylic and sulfonic compounds. And there are several approaches for us to increase the hydroelectrons in the system. The first way is to eliminate the dissolved oxygens. And then second way is to increase the pH in the reaction system. And the third pathway is we invented a novel device which is capable of increasing the hydroelectron concentration in the system. And the last way is to have external additive of the hydroelectron photosensitizers. So this is the table for us after our preliminary results. We come up with the optimized conditions with the argon environment, argon ambient 12 pH, and using our novel device as well as the sulfide as the photosensitizers. And the novel device come up with in the lab or currently under a patent application process. So here are some results for our optimized condition for the PFAS degradation. The figure that I presented here is the conventional device degradations in the optimized condition, anaerobic condition, higher pH 12. And you can see the sulfonic compounds, long-chain sulfonic compounds, PFOS, significantly decreased to more than 50% degradations. under the optimized condition. However, for the short-chain PFAS, PFBS, and PFHX, the degradation rate is still very much limited. And when we further apply our novel device into these PFAS degradations, we notice that significantly increase for the PFAS degradations within 1 hour for the PFOS, PFHXS, as well as significant drop for the short-chain PFBS degradations using our novel device. And to note is the high degradation achieved for the softening compounds and the short-chain compounds is in a clean system, which means no external chemical additives was introduced into the system. So we further introducing additives, photosensitizers for the hydroelectron photosensitizers into the systems. We see clearly for the PFBS, for example, when we add in the external photosensitizer sulfite, the PFBS in the orange bar is clearly higher than that optimized condition without the photosensitizer. And when we add in photosensitizer in the novel device, which presented in the green bar, we see significantly increase with the novel device, optimized condition, and external photosensitizers. Similar trend was observed for PFHXS and PFOS. So our conclusion is the optimized condition for the PFAS degradation is higher pH, anaerobic conditions, and the photosensitizers, and also our novel device can significantly improve the short chain and softening compounds degradations. In addition, we're shortening the long chain PFOS degradation time as well. So the conclusion for this project is the carboxylate compounds and softening compounds are degrading through different pathways under the vacuum UV degradations. And the PFAS degradation through the PFOA degrading through both high energy photons and radicals, hydroelectrons. However, the PFOS only break down through the vacuum UV generated hydroelectrons. And low oxygen, high pH, and hydroelectrons photosensitizers will significantly increase the PFAS degradation. And also, our novel device designed in our center can destroy 90% of PFOA, PFOS, PFHXS in 1 hour, and also 60% of the removal for the PFBS. So, above is the project for the novel device for vacuum UV. And now I'm going to introducing a novel adsorbent for the PFAS removal in the drinking water systems. This is the collaboration project with the chemistry department. And we are utilizing the cellulose as our novel adsorbent for the PFAS removal. As some of you might know that cellulose is the most abundant nature biopolymer in the planet. And it consists of the repetitive glucose unit. And also, this material is abundant in the plants. It can be extracted by the chemical and biological method. So the advantage of this cellulose adsorbent is because it can easily be surface modified with different charges, functional groups. And also it is low cost, has higher surface area, and also it is biodegradable, so it's environmental friendly material. Our goal for this novel adsorbent is really, as Dr. Su just mentioned, that the short chain is really a challenger. Short chain PFAS is really challenging in the PFAS remediation area. So we know that the short chain PFAS is mainly uptake by the electrostatic interactions, while the long chain PFAS is uptake by both electrostatic and hydrophobic interactions. So we were trying to functionalize this nanocellulose by modifying the positive charge on the cellulose scaffold in hope of improving both adsorptions for short chain and long chain PFAS. The synthesized process going through below flow is extracting the cellulose and surface characterization and doing the adsorption experiment and preparing the samples for the final analysis. Here are some nice, good results I like to present here is for the cellulose adsorbent for both long chain and PFAS. If you can see that adsorption in red, compare with the adsorption capacities in the black, which is commercialized carbon adsorbent. As most of you might know that the most commonly used industry is GAC. Use the surface modified cellulose, we see a significant increase of the adsorption capacities for long chain PFOA and short chain PFBA compared to the commercial adsorbent. And when we apply this material into the real water remediations, this is the real water environmental relevant samples. We apply different dose of this material from low dose 32 milligrams per liter to a high dose at 640 milligrams per liter. And we notice a large removal for the long chain PFAS, as you can see at the right end, of on the graph above C7. Almost we have above 90% removal of the long chain PFAS. However, we still have challenges for the PFAS, short chain PFAS removal, PFBA and PFBEA, even at higher dose of this adsorbent. And we were trying to further improving the short chain PFAS removal by further surface modifying this nanocellulose by increasing the side alkyl chain on the amine functional groups, as you can see here. I'm not so sure, sorry. Pointer. So we are trying to increasing the hydrophobicity on the side chain of the amine functional groups from the C4 to C12. I try my best to go to C12, yes. So when we increasing the carbon chain length on the side chain on the functional groups, we observe that for the short chain PFBA, the adsorption capacity for C12 is significantly improved compared to the C4 nanocellulose. Also, that increasement of the adsorption is observed for the long chain PFAS as well. So for this project, the conclusion would be the cationic cellulose can effectively remove the PFAS through the electrostatic interactions, which is modified on the surface of the cellulose. And the adsorption affinity for long chain PFAS is higher than the short chain PFAS. And the introduction of additional hydrophilic alkyl side chain can enhance PFAS removal, especially for the short chain PFAS removal. And also we provide a perspective of design cost-effective bioadsorbent for removal of the PFAS. Okay, so next I'm gonna briefly touch on the column experiment for the PFAS removal. Use a coupled GAC and resin rapid small-scale column test, or SSCT, which is performed by over grad students, just this here, I think. As you can see that the goal of the research is really evaluating the removal of the PFAS through the coupled granular activated carbon and the ion exchange resin columns. And this is some preliminary results we obtained. And from these preliminary results for PFBS, PFOA, and PFOS, we can see that, we can see that as we increasing the resin concentration from blue line, which is the resin concentration is 0, to gradually to the purple line as the ion exchange composition as 100%. Green line is 20% ion exchange, and red line is 50%. As you can see clearly, like as we increasing the resin content in the coupled column filter, and we observe slower PFAS breakthrough curves for all the PFBS, PFOA, and the PFOS examined in this column. So that indicating a better column performance for PFAS removal with higher content of resins incorporated. And we incorporating these learnings right now into the real water applications. We obtaining the real drinking water from West Hampton Beach, and this is the PFAS concentration level from that drinking water site. And we apply two different resin filters at the GAC resin ratio from 100-0 and 50-50. Those two different coupled resins RSCCT on the real water remediations. And we are going to do the solid phase extraction on the RSSC effluent and construct the breakthrough curves after the SPE operations. And it's ongoing work, and we were expecting results coming out soon. So with all of that information, I would thanks to the amazing research group at CCWT and also over research collaborators, as I listed below. So with that, I'll just close my presentation, and thanks for your time.